Distributed Database System presented by Rupali Banerjee. So today our topic is Distributed Query Processing. Query Processing. What is query processing? We already learned this term in our DBMS class. That is, query processing is the activity performed in extracting data from the database. In query processing, it takes various steps for fetching the data from the database. What are those steps? Those steps are parsing and translation, optimization, and evaluation. So, in centralized context, query execution strategies can be well expressed in an extension of relational algebra. That is, query here written in relational algebra. And then the main role of a centralized query processor is to choose for a given query the best relational algebra query among all equivalent ones. There are a number of equivalent query, but we have to choose the best one, the optimized one. But in case of distributed system, relational algebra is not enough to express execution strategies. Here different factors involved. First, we have to choose the ordering of relational algebra operator. Then we have to choose the best sites to process data. Means when we execute our query, then from which site we can fetch our data. That is, we can get our result immediately after processing our query. And how we can transform our data. Everything is related to distributed query processing. These are the phases related to distributed query processing. We have to learn each and every phase in detail. So our first phase is query decomposition. Here the input is calculus query on distributed relation and output is algebraic query on distributed relation. That is, the relation is distributed. That is, the table is distributed. What is calculus query? Calculus query means SQL query. It is the input. And what is the output? Output is algebraic query, that is those operations select, project, join, rename, etc. In this phase, it decomposes the calculus query into algebraic query on distributed relation. First, in this phase, it checks the global directory to retrieve information about global conceptual schema. So why global directory is needed? To retrieve information about CGS, that is centralized global schema. Why CGS is needed? That is, when we execute our query, after execution we get the result, but result means it fetch the data from the database, but in which site data is stored, we have to fetch from that site, the data we have to fetch from that site. So here it checks the global directory first to retrieve information about global conceptual schema, and actually by global conceptual schema we can check in which site our required data is stored. Here both input and output of this query, both input and output, refer to global relation without knowledge of distribution of data. Here in this phase there is no knowledge about the distribution of data. There are 4 successive steps. We have to learn each and every steps in detail later. So, successive steps are normalization, analysis, elimination of redundancy and rewriting. So, the first one is normalization. So, what is the goal of normalization? The goal of normalization is to transform the query to a normalized form to facilitate further processing. We will learn each and everything in detail. See, when we write any query, then the most important transformation is that of the query qualification. Query qualification means what? Query qualification means when we write one query, the last part of the query is where this are the conditions, that where clause. Okay, that part is called predicate. So there are 2 possible normal forms for the predicate. One giving precedence to the and is written by this symbol, and the other to the or, it is written by this symbol. We have to learn 2 possible normal form. First one is conjunctive normal form, that is first predicate P11 or P12 or P13, in this way P1n, then close the bracket and then and second condition, and then and PM1 or PM2 or in this way PMN. I want to say that when I will give one example, then this thing will be more clear for you. Another form is disjunctive normal form. In this way, you have to write just the opposite of conjunctive normal form. Here P11 and P12 and in this way P1n. Here after closing the bracket it is OR. Again for here it is PM1 and PM2 in this way. Now see the equivalence rules for logical operators and, or and not. So P1 and P2 is equivalent to P2 and P1. P1 or P2 is equivalent to P2 or P1. So in this way, you have to go through all these equivalence rules and you have to remember all these equivalence rules. Now see, not P is equivalent to P. So remember these rules so that we can apply in our example. Now take one example, then this thing will be more clear for you. Say there is one query, we have to write one query. Find the names of employees who have been working on project P1 for 12 or 24 months. So what is the query in SQL? We can write in this way. Select employee name, that is ename, from the table employee and ASC, that is the employee table and assignment table, where employee.eno is equals to ASC.eno, that is where employee.employee number equal to ASC.employee number. Okay. And ASC.pno, it is project P1 is equals to P1. And also duration is 12 or 24 months and duration equals to 12 or duration is equal to 24. So which part is our predicate? After where this part is our predicate. Now if I write this query in conjunctive normal form, how we can write the predicate part? So you have to write in this way. Employee.eno equals to AST.eno and see this symbol is and AST.pno equals to P1 and this symbol is and within bracket duration is equals to 12 then or duration equals to 24. Now our next task is to write this in disjunctive normal form by using this formula. Now think how we can write in disjunctive normal form this predicate part. I can give you one hint. We can use this equivalence rule. P1 and within bracket P2 or P3 bracket close is equivalent to P1 and P2 or P1 and P3. Okay, so by using this equivalence rule, we can convert this conjunctive normal form corresponding to its disjunctive normal form in this way. Employee.eno is equals to AST.eno and AST.pno equals to P1 and duration equals to 12, that is P1 and P2, then bracket close, then within these two there is OR. So here it is OR. Again you start one bracket, employee.eno equals to AST.eno and AST.pno equals to P1 or duration equals to 24. Now think which one is better, which expression is better, the conjunctive normal form or the disjunctive normal form. In the later form, this one, there is some redundant work. So treating the two conjunctions may lead to redundant work if common sub-expressions are not eliminated. Here we are doing redundant work. Our next point is analysis. Here we have to identify and reject type incorrect or semantically incorrect queries. So what is type incorrect and what is semantically incorrect queries? First, type incorrect. In case of type incorrect, we have to check whether the attributes and the relation names, that is the attributes in the table and the table name of a query are defined in the global schema. And second one is we have to check whether the operations on attributes do not conflict with the types of the attributes. Means the operation which we are performing should be correct. There should not be any conflict. So take one example. In this query, It is type incorrect query. See the query. Select EHAS from EMP where employee name greater than 200. Here the table name is EHAS and EHAS table is not declared in the global schema. So it is incorrect. And second error is where ename greater than 200. It is incorrect because ename is of type string. So the operation ename greater than 200 is incompatible with the type string of ename. So this query is type incorrect query. Next is semantically incorrect. A query is semantically means meaningfully incorrect if its components do not contribute in any way to the generation of the result. In case of relational calculus, when one query is written in relational calculus, it is not possible to determine the semantic correctness of that query. So, typical data structure are needed to detect semantically correctness of the query. Those data structures are connection graph or query graph and join graph. Consider this query. Select ename, this ename, and responsibility, that is RESP from EMP table, ASC table and project table, EMP, ASC and project table, where emp.eno equals to asc.eno, emp.eno is equals to asc.eno, and asc.pno equals to project.pno, asc.pno equals to project.pno, and pname equals to cad or cam, pname equals to cad or cam, and duration greater than equals to 36. Here duration greater than equals to 36 and title equals to programmer, and title equals to programmer. Now this is the query. Now we have to check whether this query is semantically correct or not. How we can check? See, first we have to draw query or connection graph. How we can draw query or connection graph? See, nodes represent operand or result relation. So nodes represent operand or result relation means what? These nodes are table C, EMP, ASD, project, and this is the result. Okay. Edge represent a join if both connected nodes represent an operand relation, otherwise it is a projection. So edges, employee and ASD table, EMP and ASD table, EMP and ASD table. So it is emp.eno equals to asd.eno, asd and project table. It is asd.pno equals to project.pno, asd.pno equals to project.pno. Okay. Otherwise, it is a projection. Means we select pname equals to catcam. From which table? Project table. So pname equals to catcam. And duration greater than equals to 36. So it from which table? AST table. Duration greater than equals to 36. It is self loop. These are self loop. And title equals to programmer. So title equals to programmer. From which table? Employee table. In this way, first you have to draw this query or connection graph. Now, see here another thing. Select ename RESP. So, from where you have to select ename and RESP? From employee table and ASC table. Okay. And this should be goes in what? These are goes in result table. So, ename and RESP. Now, this is our query graph. First, you have to draw the query graph. Now we have to learn how to draw join graph. What is join graph? It is the subgraph of the query graph. But here we only consider the joins. So the joins are ASC table with EMP table. It is emp.eno equals to asc.eno. Another is ASC table with project table, asc.pno with project.pno. Now see, all the tables or all the relations are connected. Since the query graph is connected, the query is, we can say it is semantically correct. Means all the relations are connected. So we can say that the query graph is semantically correct. Now take one example where it is semantically incorrect. See, first we have to draw the query graph. Select ename RESP, ename RESP. From table EMP, ASC and project. from table EMP, ASC and project, where emp.eno equals to asc.eno, where emp.eno equals to asc.eno. There is one join. And pname equals to catcam. Pname equals to catcam. Okay, self loop. And duration greater than 36. Duration greater than 36. And title equals to programmer. Title equals to programmer. Now see, there is no join between ASC and project table. Okay. Since the graph is not connected, the query is semantically incorrect. Because there is no connection, so we can say that this query is semantically incorrect. Then what should be the solution? How can we make it correct? There are three possible solutions. First, reject the query, means don't consider this query. Otherwise, you can make one implicit Cartesian product between these two tables, ASG table and project table. Or you can conclude from the schema the missing join predicate, means you can make one join between asg.pno is equals to project.pno. In this way, you can make these three solution. Types of questions comes in your university exam. Here the answer is given. Elimination of redundancy. We have to simplify the query by eliminate redundancies, that is the redundant predicates. There are some well-known idempotency rules. The rules are given below. See, these are the rules. P and P is equivalent to P, P or P is equivalent to P, P and true is equivalent to P, P or false is equivalent to P. In this way, go through these rules. Now, using these rules, how we can eliminate redundancy? We will take one example, then this thing will be more clear for you. Consider this query. Now, we have to simplify it. How we can simplify it? First, take the predicate. So, predicate portion is after where this portion is predicate. Okay. So, the simplification proceeds as follows. Let P1 be title equals to programmer and P2 be title equals to electrical engineering and P3 be ename equals to JEDO. Now, how we can write this qualification? We can write this qualification in this way. First, employee.ename equals to JEDO, that is P3, P3, then or, opening bracket, not, employee.title equals to programmer, that is P1, and then bracket start. Employee.title equals to electrical engineering or employee.title equals to programmer, that is P2 or P1, bracket close. And not, employee.title equals to electrical engineering, that is P2, bracket close. In this way, we can write the qualification. How we can eliminate redundancy? First, I am applying rule 5 for this underlined portion. Now see, within bracket there is or and outside of the bracket there is and. Here also within bracket there is or, outside there is and. So it is equivalent to P1 and P2 bracket close or P1 and P3. So I get this expression. Again for this expression, within this bracket there is or and outside it is and. That again I can apply rule 5. So I get this expression. I repeat, within bracket there is or and outside there is and. So here this is one expression, this is one expression. In between these two expressions there is or and outside there is and. So again I am applying rule 5 and I get this expression. Now by applying rule 7, that is P and not P equals to false. Here it is not P1 and P1. And also here see P2 and not P2. So these portions are false. So I get this expression by applying rule 7. And see, P and false is false, means and false means false. So here this expression is false and this expression is false. By applying rule 5, we get P3 or this portion is false and this expression is also false. So P3 or false or false. So P3 or false means by applying rule 4, it is P or false is P. So it is only P3. Okay. So P1 be the title equals to programmer. We already learned P2 be the title equals to electrical engineering and P3 be the ename equals to JDO. So we can write in this way and the simplified query is select title from EMP where ename equals to JDO, only P3. In this way, we can eliminate the redundant expression and we get easily the simplified query by using these rules. Types of questions comes in your university exam. One is solved for you. And the last step of query decomposition is rewriting. Here, in the last step of query decomposition, rewrites the query in relational algebra. For the sake of clarity, represent the relational algebra query graphically by an operator tree. So first we have to write the query in relational algebra, then we have to represent graphically by operator tree. There may be several operator tree, but there may be several calculus query, but we have to choose the better ones. Take one example, then this thing will be more clear for you. Find the names of employees other than J. Doe who worked on the CAD/CAM project for either 12 or 24 years. So what should be the SQL query? Query should be like this: select ename from EMP-SG project where emp.eno equal to sg.eno and sg.pno equals to proj.pno and ename not equals to jdo and pname equals to catcam and duration 12 or 24. So if I represent this query in relational algebra and after representing it, if I draw the query tree would be like this. How we can draw the tree? First, relations are leaves, that is from clause. So from EMP, ASG and PROJ. So PROJ, ASG and EMP all are leaves. Result attributes are root, that is select clause, select ename. So project ename. Intermediate leaves should give a result from the leaves to the root. So first we have to join ASG table with EMP table. emp.eno equal to sg.eno, join this by eno, and then sg.pno equals to project.pno, join this by pno, then select ename not equals to jdo, then select pname equals to catcam, then select duration equals to 12 or duration equals to 24. After that, project ename. In this way, you can draw the query tree. Next step is data localization. Here input is algebraic query. We already learned how we can draw the query tree, etc. So the input is algebraic query on global conceptual schema. And what is the purpose of this step? The purpose of this step is here the main role of the second layer is to localize the query data using data distribution information in the fragment schema. That is, in distributed database, total relations are fragmented and stored in disjoint subset called fragments, each being stored at a different sites. So total relations are fragmented and stored in different sites. So this layer determines which fragments are involved in the query. That is, when we are writing the query, we have to fetch some data. As a result, we have to fetch some data. In which fragment we can get the result, we can fetch some data, this layer determines. So this layer determines which fragments are involved in the query and transform the distributed query into a query on fragments. So how translating a global query is done? See, in distributed database, a single global relation is sometimes fragmented. So there is one total relation, global relation, it is fragmented and it is distributed in different sites. These fragments are deployed on distinct sites, moreover, to ensure processing locally. Sometimes a relation or a fragment gets replicated on. So, first, there is one total relation. It is fragmented first and it is distributed in different sites. There may be replications. A query, on the other hand, is issued by a user or an application which is not aware of the existence of fragments allocation. When one user comes and trigger a query, they don't know that whether your total global relation is fragmented or distributed, etc. etc. User is not aware of the existence of fragments allocation. That is, the global query for its successful execution must get decomposed into fragment queries. Means what? Take one example. If the global query is select star from student, this query must be decomposed into certain queries, which take us their operands, the fragments into which student relation has been fragmented. That is, when I decompose this query, that is how we can write the fragment queries. We can write in this way. Select star from student 1, that is the student relation is fragmented. So the fragmented queries are select star from student 1, select star from student 2, select star from student 3. In this way, select star from student n. So, for the execution of this fragment query, it is imperative that the information about the fragment replication and allocation must be obtained. So, we already learned that query tree provides a more practical representation of queries in which expression manipulation is easier. So, if I draw query tree, then expression manipulation is more easier. And we already learned in the query tree, the leaves represents the relations and each node represents an operations. So take one query, select snum from supply, comma department where supply dot department name equals to department dot department name and area equals to north. So two tables are there or two relations are there, supply and department. They are joined by department name. So join department name equals to department name and area is north. So area, select area equals to north and then you have to project what? SNAM. So project SNAM. So here the global relations are supply and department. Now this is case 1 in case of global relation. Now we have to consider the case 2. What is case 2? We have to consider fragmented relations. Here, supply table are fragmented and department table are also fragmented. So, it is supply 1, supply 2, supply n. It is department 1, department 2, in this way department n. And there is one union. And remaining query is same. But this is not the optimized one. We have to consider the optimized one. So, how we can get the optimized tree? We already learned in our DBMS class how to get the optimized tree. So, for getting the optimized tree, first you have to select from the department table area equals to north. So, from department 1 table you have to select area equals to north. From department 2 table you have to select area equals to north. In this way, from department n table you have to select area equals to north. And then you have to do union. So, this is the optimized one. Here, these queries fragments with optimized result. Reduction for primary horizontal fragmentation means after fragmentation, how we can again generate a generic query. Means what? Take one example. Let EMP table is horizontally fragmented into EMP1, EMP2 and EMP3. EMP1, EMP2 and EMP3. So, in case of EMP1, select employee number less than equals to E3 and employee number E3 to less than equals to E6 is employee 2 and employee number greater than E6 is employee 3. Means we have to select those employees whose employee number is less than equals to E3. Those tuples are stored in EMP1 and employee number less than equals to E6 and greater than E3, those employees tuples are stored in EMP2, and where employee number greater than E6, those tuples are select and stored in table employee 3. Again, for ASG table also, see, ASG table is fragmented by two tables, ASG1 and ASG2. In case of ASG1, employee number is less than equals to E3, and in case of ASG2, employee number is greater than E3. Now, what is the approach? Approach is replace in all queries. We have to replace EMP table by employee 1, employee 2 and employee 3 table. And we have to replace ASG table by ASG1 and ASG2. And after union, we get the whole query. So in this way, the total table EMP is replaced by these three table, these three fragmented table, and total table ASG is replaced by these two fragmented table. But we have to remember unnecessary work can be eliminated. Means, see, if we join employee 3 table with ASG 1 table, then here we select those employees whose employee number is greater than E6. And for ASG1 table, we select those employees whose employee number is less than equals to E3. So when we join these two tables, this will give empty result. So unnecessary work, you have to eliminate it, those works. So when we eliminate this unnecessary work, then we can get accurate result, we can get proper tuple. So those joins are, we have to join employee 1 with ASG1, employee 2 table with ASG2 table, and employee 3 table with ASG2 table. Our next step is global query optimization. Here the input is algebraic query, but it is fragmented. So algebraic query on fragment is the input of this phase. Here the main objective of this phase is to determine an execution strategy close to the optimal solution. Means we have to determine which should be our execution strategy so that we can get the optimized result. There are many similar queries. They can be ordered based on cost function. How we can determine cost function? Cost function is decided using terms such as time units, computing resources. What are the resources? Like disk space, I/O, CPU cost, communication cost, bandwidth, etc. We have to select the best optimum ordering of operators execution cost, and then we have to first calculate the execution cost and we have to select the best optimum ordering depend upon the execution cost. Also, these decisions depend on fragment allocation and also fragment statistics. And finally, we get the optimized global query. One aspect of query optimization is join ordering through the semi-join operators. What is semi-join operation? We already discussed later in this series. So the output of this phase is the optimized algebraic query with communication operators including fragments. The last phase is local optimization. Here, those fragments that are involved in the query is considered. Means when the query is written, we get the answer from particular fragment and that fragment are stored in different sites. So those participating sites are involved. Here each subquery executing at a particular site called local query on that particular site. This query is also optimized using local schema and then executed there. At this time, the algorithms to perform the relational operators may be chosen. And what is the output? Output is returned to the site where our query is triggered, that is query is generated. Types of questions comes in your university exam. Go through these questions. And if you have any query, you can ask in the comment section. for getting more and more updates, please like, share, and subscribe my channel. That's all for today. Thank you.